Hello everyone, welcome back. In this section, we'll talk about the ratio and root test. Okay, so we can say we have learned a lot about the divergence and convergence of series, right? The tests we have developed so far to determine whether a series converges are powerful, but they all have limitations. We now consider two additional convergence tests for general series: the ratio test and the root test. Both tests are used frequently throughout the next chapter, okay? As in previous section. So these tests determine whether an infinite series converges, but they do not establish the value of the series. Let's jump on with the ratio test theorem. Let the sum of A sub k be an infinite series, and let R be equal to the limit of absolute value of A sub k plus 1 divided by A sub k. Sorry, this is a typo. Let me correct this one very quick. A sub k plus 1 divided by A sub k as k approaches to infinity. 1, if R is less than 1, then we said the series converges absolutely, and therefore it converges by absolute convergence theorem. If R is greater than 1, including R is equal to infinity, the series diverges. 3, if R is equal to 1, the test is inconclusive. So let's use the ratio test to do the first example that we have. Okay, you can see we have the sum of from k is equal to 1 to infinity, 10 to the power of k divided by k factorial. So it says solution. We can see this series is positive, right? It's a positive. This series have what? Positive term. All of the terms are positive. So we first set our A sub k, which is 10 to the power of k divided by k factorial. This means A sub k plus 1 will be 10 to the power of k plus 1 divided by k plus 1 factorial. So now our limit of absolute value of A sub k plus 1 divided by A sub k as k approaches to infinity, because both series are positive. We don't need the absolute value. We can just set is equal to the limit of 10 to the power of k plus 1 divided by k plus 1 factorial divided by A sub k, which is 10 to the power of k divided by k factorial as k approaches to infinity. If you have a fraction divided by a fraction, you take the numerator and you multiply by the reciprocal of the denominator. So this will give us the limit of 10 to the power of k plus 1 divided by k plus 1 factorial times k factorial divided by 10 to the power of k as k approaches to infinity. So now we simplify, right? So you will see 10 to the power of k plus 1 and 10 to the power of k will cancel out. It will left 10 to the power of 1, right? k plus 1 factorial and k factorial will simplify to the left, k plus 1. So this will just give me the limit of 10 divided by k plus 1 as k approaches to infinity, and this limit is 0. So we can see, we will conclude, because r is equal to 0, which is less than 1, then that means what? The series converge. By the ratio test. Right? Okay, we'll do the same thing for B. Again, B, we have to establish our A sub k and A sub k plus 1. So our A sub k, which is negative 1 to the power of k, times k to the power of k, divided by k factorial. And A sub k plus 1 will be negative 1 to the power of k plus 1 times k plus 1 to the power of k plus 1 divided by k plus 1 factorial. So now let's find our limit. The limit of absolute value of A sub k plus 1 divided by A sub k plus A sub k as k approaches to infinity will be equal to the limit of my A sub k plus 1 is negative 1 to the power of k plus 1 times k plus 1 to the power of k plus 1 divided by k plus 1 factorial. Everything divided by A sub k, which is negative 1. Don't forget the absolute value. Okay, negative 1 to the power of k times k to the power of k divided by k factorial as k approaches to infinity. Now we will simplify this. You can take a scratch paper to do the simplification yourself, okay? And this will give me the limit fraction divided by fraction. So we take the numerator, which is negative 1 to the power of k plus 1 times k plus 1 to the power of k plus 1 divided by k plus 1 factorial times the reciprocal would be k factorial divided by negative 1 to the power of k times k to the power of k. Right? So we can see first the absolute value cancel the negative 1 to the power of k plus 1, and so the absolute, I could do that since the first step, okay? The absolute value Turn negative 1 to the power of k plus 1 and negative 1 to the power of k. And also, once I do that, sorry, k approaches to infinity. So once we do that, and again, we are not done. So you can see, basically have k plus 1 to the power of k plus 1 divided by k plus 1 factorial times k factorial divided by k to the power of k. So we'll see k factorial and k plus 1 factorial, we cancel out, it will left what? K plus 1, right? K approaches to infinity. And then we will have the limit. So we'll be left with k plus 1 to the power of k plus 1 divided by k plus 1 that is left from the k plus 1 factorial times k to the power of k. So if we look closely, we can see k plus 1 to the power of k plus 1, we know that is same thing as what? K plus 1 to the power of k times k plus 1, right? So k plus 1 and k plus 1 will cancel out. So it will left the limit of k plus 1 to the power of k divided by k to the power of k as k approaches to infinity, which is same thing as what? K plus 1 divided by k to the power of k, right? K approaches to infinity. So now, you can find this limit by applying the ln, right? We have done this so far, and you will see this limit will give me, this is same thing as the limit of 1 plus 1 divided by k to the power of k as k approaches to infinity, which is what? E. So this limit will give me E. We can see from there, R is what? R is equal to E, which is greater than 1. That means what? The series diverges by the rules. By the ratio test, I said the rules. By the ratio test. Right? Of course, an alternative way to find this quick was doing the divergence test. Right? We could do the divergence test. So again, let me write this in red. we could the limit k to the power of k divided by k factorial as k approaches to infinity, which is infinity, right? And then use the divergence test to reach the same conclusion. Use the divergence test, which that is series diverge. Okay. C, we are asked to find to check if this series converge again. So same thing, write your a sub k, which is negative 1 to the power of k plus 1 times e to the power of negative k, k squared plus 4, right? And a sub k plus 1 will be negative 1 to the power of k plus 2 times e to the power of, you put the negative in parentheses k plus 1 times k squared, so which will be k plus 1 squared plus 4. So then I will write my limit of absolute value of a sub k plus 1 divided by a sub k as k approaches to infinity will be equal to the limit absolute value of negative 1 to the power of k plus 2 times e to the power of negative k plus 1 times k plus 1 square plus 4 everything divide by negative 1 to the power of k plus 1 times e to the power of negative k is k squared plus 4. Because of the absolute value, the negative 1 to the power of k plus 1 and negative 1 to the power of k plus 2 will cancel, right? Because of the absolute value. So it will left it of e to the power of negative k plus 1 times, I'm going to distribute this k plus 1 square, so which will give me k square plus 2k plus 1 plus 4, so that will become plus 5, divided by negative 1 to the power of k plus 1. Oh, sorry, we cancel that. Power of negative k is k squared plus 4 as k approaches to infinity. So we can see we can simplify e to the power of negative k plus 1 and e to the power of negative k. If I simplify this, it will left what? E to the power of negative 1. So I will have e to the power of negative 1, the limit k squared plus 2k plus 5 divided by k squared plus 4 as k approaches to infinity. Okay, if you want, Nick, why I put this one before the limit, because e to the power of negative 1 is a constant, so I can put that before the limit, right? So now, what is this limit? We know we have done this type of limit so many times. So this is same thing as k squared divided by k squared. The dominating term of the numerator is k squared. The dominating term of the denominator is k squared. Because k is approaching to infinity, those two terms are the dominating terms. So this limit will give me what? E to the power of negative 1, because this limit is 1, right? This is 1. So what do we conclude? So R is what? So R is equal to e to the power of negative 1, which is same thing as what? 1 divided by e, and that is less than 1. Therefore, the series converge. Absolutely. By the ratio test. Which imply that the series converge. It converges. And that's it for the ratio test. So now let's talk about the root test. So let the sum a sub k be an infinite series, and let rho be equal to, so rho is a Greek notation. So if you want call it p, it's just a notation, okay? Rho is equal to the limit of root k root of absolute value of a sub k. Okay. One. If rho is less than one, the series converge. Yes, absolutely. And therefore, it converges by absolute convergence theorem. If rho is greater than one, including rho is equal to infinity, then the series diverges. And if rho is equal to one, the test is inconclusive. Again, so again, let's jump to the first example to solve this one. So you can see in this case, we have this use the roots test to determine whether this following series converge. So solution, the required limit will be what? Rho be equal to the limit of k root of absolute value of 3 minus 4k squared divided by 7 times k squared plus 6 to the power of k as k approaches to infinity. So, and to the power of k will cancel out. So these two will cancel out. Let me write k correct. Okay. Right? And then it will left what? The limit of 4k squared minus 3 the absolute value of 3 minus 4k squared divided by k approaches to infinity. But you know, k start from 1, right? And because of the absolute value, this limit will be what? Absolute value of negative 4 divided by 7, which is 4 divided by 7. So because rho is equal to 4 divided by 7, right? Which is what? Less than 1. Then we said what? The series converge absolutely by the roots test. And therefore, it converges, right? Imply is converges. Same thing we will do for B. So for B, again, rho will be equal to what? The limit of k root of absolute value of -2 to the power of k divided by k to the power of 10. As k approaches to infinity, which is, again, because of the absolute value, we will have k root, k root and k will cancel out, so it will left, because of absolute value, it will left 2 divided by k to the power of 10 divided by k. You write this correctly so you can see. That's what it will left, because this is k root. So it will left k to the power of 10 divided by k. Do you see it? As k approaches to infinity. So let's go step by step so you know. This will be what? The limit of 2 divided by k to the power of 1 over k to the power of 10 as k approaches to infinity. So we know this is 1. The limit of k to the power of 1 over k as k approaches to infinity is equal to 1, right? Because 1 divide, right? We know you can apply ln to find this one. It's already proven, so this limit will give me what? 2. And we can see my rho is equal to 2, which is greater than 1. Then we can conclude what this series diverges by the root test. Again, we could use the ratio test for both series in this example, okay? We could use the ratio test. The ratio test for both examples. So try that. And for both this example. So try that at home. That's the end of this section. I will see you in the next one.